Okay, welcome to today's Coreform webinar. It's an IGA update today. We'll wait just a couple of minutes to let everyone join. Again, I'm Matt Cedarberg, CEO of Coreform. Clint Nicely is presenting for us today. He joined Coreform just recently from Raytheon. And we'll be giving an update on our IGA solver. We are continuing to develop functionality here, and today we'll be talking more about the new model tree probe output and give a linear statics example. So with that, I'll turn the time over to Clint.
Hey, thank you, Matt. So thanks again, everyone, for joining us today. We're really grateful for the time that you take and watching these webinars. It's our intention to give you a good information, good use of your time. So today we're going to be going over sort of briefly, again, just to introduce if you're not familiar with what Coreform IGA is, what we're doing, what we're hoping to achieve. We'll be then going over some of our recent developments that we've implemented into Cubit and to our Coreform IGA solver. Those are the model tree in Cubit and the probe output. And of course, we'll be using linear statics to solve our analysis today. In that, we'll be demonstrating the use of the Cubit CAE model tree, and also we'll be looking at the probe output feature as well. So again, just like I said, these webinars are hosted to bring everyone who's watching this up-to-date news on how we're developing our Coreform IGA solver. We are building a isogeometric analysis solver from the ground up to be built for isogeometric analysis solves first. So this is apart from building an FEA solver and then converting it to an IGA, we're building an IGA first. Again, throughout the webinar, please feel free to ask questions. We encourage this. Please stay interactive. We'll answer them as we see them if there's a break in the time. And we will, of course, if we hadn't got to them, we'll have time for questions at the end of the webinar as well. We also want to be able to hear what you find difficult about your finite element analysis and how you think isogeometric analysis might be able to solve that for you. One of the things that drew me to isogeometric analysis when I was working at Raytheon was we were driven a lot of times by fatigue requirements, where little tiny fillets, small details in the model would always drive large geometry changes, would drive us to increase weight, change materials at the last minute, or some other changes that would cost us time, money, effort, which to a program on in Raytheon, time is money always. So anytime you can make the process smoother, get problems solved earlier, run your analysis with less need to prepare and to simplify a model, these are all things that would be of benefit. And what I saw in isogeometric analysis was the ability to keep all of these features that the designers put in the model and are going to be there in the design when it's made in real life, but sometimes are simplified out in the finite element analysis. In isogeometric analysis, the idea is that you would be able to keep all of these details and get increased fidelity at the same time from your analysis. So that's what drew me to this. And I wanted to make sure that as this technology grew, I would be aware of it. I could learn from it as it grew, and I would be able to pick it up and run with it when it was ready to be used in my industry. So that's what I'm hoping you all are here for today. And with that in mind, let's go forward into a brief description of Coreform IGA and sort of broadly isogeometric analysis in general. So the idea for isogeometric analysis is that for a long time, the realm of computer-aided design and computer-aided engineering were sort of separate but parallel paths. They were created sort of in different decades, and while they were working together, they never really coincided with the same technology. They each used disparate technology paths. And isogeometric analysis sought to merge those two paths together in the use of the spline functionality. So again, as I said before, isogeometric analysis, its hope was to allow you to retain all the geometric features that are within a CAD program that you would run in your analysis. So here on the screen, we have a flow chart that demonstrates how much time is spent within a particular activity in a finite element analysis. You'll notice that there is a big chunk of time spent on analysis on model creation and geometry condition and geometry decomposition and meshing. This all has to do with getting your model in, simplified, meshed, and ready to run. So the goal of isogeometric analysis is to make these steps go to almost nothing, to where if there is any work that needs to be done on there, it is because the user desires to do it and not because it is needed to run an analysis. So we're hoping to, and what we're building our tools to do is we're decreasing the meshing time, we're increasing the simulation accuracy through the introduction of spline basis functions. And because of these things, it will radically accelerate your design process, because as we'll show today through our model tree and through our model creation, that now Coreform IGA has separated the need to have a mesh on your CAD geometry, but rather a mesh that surrounds your CAD geometry. So here is just a little bit of where we stand today. Currently, hex-based FEA, tetrahedral-based FEA, meshless methods, and then there's a new one called kind of voxel methods, which each of them has their own little category of accuracy and speed. Hex-based can be slow, but its accuracy is deemed by current FEA standards very high. Tet-based FEA is fast. You can tet bomb a very complicated object, and you can get almost as good fidelity these days as you would out of a hex-based FEA, but you're going to have a lot of elements to deal with. Meshless is a growing methodology for using it, but again, it's really fast because you don't need to worry about meshing it, but it's not quite, it still needs to get a little bit more accurate. And then voxel-based is even faster than that, but that speed is always at the sacrifice of some accuracy. Coreform IGA, we are introducing a new category, a new realm of accuracy in the introduction of these smooth splines functions. And both sides here is we could do body fit use splines, which coincides more with like a hex-based FEA where the mesh is on the CAD geometry. We also, and on the other side of that is immersed splines, where the discretized geometry envelopes your CAD geometry, and you no longer have the necessity of having your mesh on your geometry. It merely needs to surround it. And with these introduction of these smooth functions, we're able to get higher accuracy than even with hex-based or tet-based FEA, and we're able to do things much, much faster with the immersed spline than we have been able to do before. And this is what we're calling Coreform IGA. So this is a little bit what this looks like now that we're sort of talking about it. Body fit, again, on the left here is where the mesh, the nodes of the mesh directly line up with the surface body, with the surface of the CAD geometry. A traditional immersed takes that mesh and it just surrounds the CAD geometry in a mesh. And of course, we can also do in between, where we have capabilities of doing a semi-body fit or a semi-immerse, where if you wanted to do somewhere in between, make sure that your model runs as smoothly and as quickly as possible, but with the least amount of effort, you can tune anywhere in between as well. This immersed meshing capability allows us to do a very complex analysis geometry with a very simple mesh. So here is a lattice geometry that's being pressed from the top, and this is just 8,000 cubic U-spline elements in a block. So this is a 3D part. It's a block. The only thing, it's immersed in a mesh, and you can see on the gray example here, there are mesh lines going back and forth, up and down. And we have a quick little video that shows it being compressed. So we now have separated the need to have the mesh on the body to now being the mesh just enveloping, which greatly increases the speed at which you can build and create your models and analyze them and get to the analysis faster, which is really what we're all trying to do. We're all trying to get the answers to solve the problems that we need to solve and make sure that we meet the requirements that we're having to run our analysis against. So let's see. So we were here to see a demonstration of the Cubit model tree. So we're going to step out of here for a moment, out of the slide deck. And let's see, I just want to make sure, let me know if my presentation here drops or anything, if we're still looking at it. But this is, we're now looking at a window of Cubit with the component that we're analyzing today. This is a NIST component, and it has lots of curved features, many things that we would, as an analyst, like to remove. It seems that we've also gotten this part with fillets around the entire radius of it. It seems that as though that the design engineer that had this before us got a little overzealous and actually put in handling fillets, which is one of his requirements. So he decided to model it. Well, to an analyst, that is nightmare fuel, because we now, in a traditional FEA, would have to go in and simplify every single one of these rounds all around the perimeter of the top and the bottom. And we would also then need to go in and fill in these other fillets at the base of this hexagon pedestal. And we might also remove these chamfers at the top of it as well. For some areas that we may not be interested in, some of these holes might be filled in as well to just increase or decrease the mesh complexity. But for our case here, we don't necessarily need to do that. All we would need to do is just surround it in a mesh. But before we get to that, let's go over here. So we have over on our left here is our new model tree. And you would access this in Cubit by going to View. And at the bottom, almost on the bottom, there is this option that you can click called the CA model tree. Once you enable that, a tab will open up here on the bottom. You can click on it, and you can now begin to import quantities in here to construct your input deck for Coreform IGA. It's a fairly easy, fairly straightforward. Our goal is to have one-to-one correspondence for everything in the model tree to everything that will end up in your input deck. So here, for instance, you would type in a description, NIST component. Coreform IGA version, we had put in 2022.4, and our label is just linked NIST. So one of the things that you would want to put in first in any sort of structural analysis is you'd want to put in your material properties. So once you put in the material property, it will expand and you'll have your options of your current material models. Right now we have linear elastic, elastic, and isotropic plasticity. So let's just do linear elastic. So we're going to do this in English units. I'm sorry if that for anyone that might be out of the United States, but English units is in pounds, inches. And so we'll do that. Steel is 29e to the 6th psi, Young's modulus, and the Poisson's ratio is 0.28 generally, just for a generic type of steel. Now, you'll fill out the rest of your model tree as you would, but I'm not going to bore you with going over that on my own. So we have a quick video here demonstrating the construction of the model tree and the construction of that NIST component in a timer, showing that what we're aiming to do here is to do this very, very quickly. So as you can see here, now we've enveloped our NIST component. We're now building our U-splines. and we're fitting the U-splines to the enveloping body, which is the yellow, and then we begin to fill out our model tree. And again, everything here in the model tree corresponds one-to-one with how it will be output in the input deck. And if you have a current input deck, yeah.
Clint, do you want to mention what the
Yes.
format for the input deck is?
The format is in a JSON 5 format.
And so is that a binary?
It is not a binary, no.
So essentially any user can open up a text editor and see the input file and edits. Is that correct?
Yep, that is correct. And so the input deck that you just saw created, fast forward in about 35 seconds, which was done in real time in a little bit less than 10 minutes. You're now looking at it here. So here again, we have that NIST component 2024. Looks like I gave it a different label in this one, called it the webinar. Here we have our steel, all of the pieces, parts that we wanted to. We have our function definition for when we want our loads to come into effect. And we have some other aspects of our input deck that are all there when you can load them into your model tree. One other aspect of our model tree, or of our Coreform IGA solver that we wanted to introduce today, was the ability to have a probe output. So this is a capability that you can probe any location in your CAD geometry to have it output any sort of field data that you would want, whether that be stress, displacement, anything that we currently offer, you can have output at that location regardless of the mesh discretization that is occurring at that point. So it doesn't need to be at a nodal location. It doesn't need to be at an integration point. It can be at an arbitrary location. And that is one of the other features today. And that is down here at the bottom, right here. This location coincides to, I believe, the center of this surface right here that I have highlighted. So once we have this, we can then come down to your solver. Let's see. And you can submit your job. And it will run. This particular one takes a few minutes to solve. I'll let this churn here for a bit before we skip over to, we're not going to sit here and watch the whole thing solve. I have the results for you pulled up somewhere else, but this is what it looks like when you submit a Coreform IGA analysis. Once that solves, which this one only takes a few minutes to solve, you'll be given some VTU output that you can then visualize in ParaView. So this current one that we're looking at right now is the displacement. This model, we were pressing down on the surface of this hexagon pedestal and also pushing on this large flat surface as well. So that's why you're seeing a majority of the displacement occurring in this center piece, and we were holding it fixed at these 4 exterior points. Looking at stress, we see right now this is an output of the integration points that we have. Our probe location was in right here in this location for our that we were seeking to probe the output. And once we have this, so now that we have the stress, but we also can go back now and we can check to see the output, that the probe output, when you call it, it also produces another output file for you, and it produces a file that's an H5 file. So this is an HDF5 file. You can pull this up in any HDF5 and any HDF viewer. This can also be folded into any sort of Python scripting to expedite any sort of post-processing that you would want to do with any of your data. So for our particular location, that stress that was popping out there was a maximum principal stress of about negative 2.3 KSI, which if, according to the pair view peak output, the peak output was about 2.5 PSI. So that rhymes nicely with the peak output being that this probe output was a little bit lower than at the top, and the stresses in this location did fade as they went down to the bottom. So that leads us to the end of our introduction of the CA model tree and the probe output. Again, as I hope everyone was thinking about how Coreform IGA isogeometric analysis in general would be able to help solve your problems, help you expedite your analysis, help you get better results from what you're currently looking at, helping to get those results faster and more efficiently. If you do have those thoughts, we'd love to hear about them and to be able to continue a conversation with you about how Coreform IGA can help to solve these complex problems. So with that, that's all that we have prepared today, and we would be happy to have any of your questions.
Clint, thank you so much. It was well prepared and
being here.
An exciting stuff to share. And thanks also Greg Vernon, unannounced as well. Thank you for your help. Okay, so now if you have any questions, feel free to add them into the Q&A panel, and we can answer them. So one question that we've got, what type of materials does Coreform IGA support today?
So we do have the material models that we show in the model tree, linear elastic, and isotropic plasticity. Greg, please correct me if I'm wrong, but I believe we can also do a user input material models as well at this point in time. Is that correct?
Yes, that is correct. We don't have any examples of that we've shared of using that user material interface, but we can work with customers to explore that for a given material.
Okay, thank you. So another question, from your experience, Clint, or Greg, meshing and preparing models, what would be the time comparison between the prep time to immerse that model versus mesh that using traditional FEA?
So I think if it depends on the experience of the analyst, if that part that we were looking at today could take anywhere, to simplify, could take anywhere from 10 minutes to 30 minutes depending on the experience of the analyst in traditional a body fit approach.
Okay. Yeah. And of course, if there are cases where there are certain features that you can't defeature because it's a location that has failed or you're concerned about, that can make then the meshing challenge more difficult with the traditional body fit approach. And so a couple of us were looking at that geometry and thought, if we were to not do any defeaturing at all, I mean that's potentially a day-long or multi-day long effort to mesh without defeaturing. And certainly from, if you're taking the flex approach of just immersing it in a trivial to mesh background grid, I mean, it's a matter of seconds to have it meshed.
Thank you. Another question, does Coreform IGA allow the use of 1D connection elements like RBE2 or 3?
So that's something that we're actually working on. We don't support that yet, but we do support it within the theory, the framework of Coreform IGA is built upon. We do have a tie constraint. It's just come online, and we're getting ready to release with our next version. And we also plan to support kind of these RBE2s and RBE3s in future versions. And again, it's a very similar approach to what we showed today, where unlike traditional FEA, where these RBE2s or RBE3s connect, nodes to nodes or a reference point to nodes. The RBE2s and 3s that we have in Coreform IGA are independent of the mesh.
Great, thank you. Another question, is it possible to have multiple parts and contacts?
Yeah, so kind of along what I was kind of mentioning with tie constraints, that is, we do have surface-to-surface contact that's in kind of an experimental development stage, as well as a tie constraint. We do support multiple parts. Again, right now we're still kind of building this code from scratch, and so we're a bit more experimental in those areas. But that is possible today with Coreform IGA, and it's something that we'll get better at as we continue to develop the code. So stay tuned for that. Hopefully we'll have some examples soon, and maybe we'll see those in some upcoming webinars.
Great, thanks, Greg. Just a question from Yongzhen. Thanks for the introduction. Does the IGA solver support structural mechanics such as plate or shell analysis?
Yeah, so I guess, Clint, do you want to take this one?
I think I was just going to answer the simple question of yes, it does. But please expound upon that.
Yeah, and I guess the one caveat to that is that we are developing. We have done some theoretical developments for various different shell formulations. They're not exposed yet to an end user in Coreform IGA, but we have run several problems. I mean, multiple problems with shells in our kind of experimental code base. So yeah, I'd say, I guess, stay tuned for results on that. The Flex IGA approach extends nicely to shells, and so that's actually one of the areas that we're really excited about.
Mm-hmm. I think one of the reasons that we talk internally about why we take time to do these webinars and why each of you might take time out of your day to come watch these at this stage of our solver. And that's one of the main reasons, is that there's so many capabilities that are just kind of waiting to come online. And part of the way we prioritize is based off of interactions that we have with users. And so if any of these are of particular interest to you, or as Clint was mentioning, if you have any impractical problems that you just are sure there must be a better way to do with simulation, if any of this is resonating, we'd like to talk with you, and we can accelerate some of those developments.
And Clint, could you go back one slide to the forum slide?
Yes.
And so, especially with these questions, we highly encourage you to come to our forum, and there's a Coreform IGA topic thread, and we encourage you to, if you ask questions there, and we can, through the forum, we can actually give you more detailed responses through the forum. So we encourage your participation there, and we'd love to interface with you through that medium.
Yeah, so another question just came in: how can we collaborate? We collaborate, I guess. So just the first question is just to get in touch and have a conversation. And so we're fairly easy to get a hold of. You can post on a forum, email sales@coreform.com. We're still a small company. There's only about 30 of us, and so that will come. I will see that as it comes in. Or you can just email me directly at matt@coreform.com. But then as far as how our collaborations go, we just sort out to see what your problems are. Usually if there's a way that you can satisfactorily solve it today, then there's probably no need for us to interact because you're already solving your problem. But if it's a significant pain, then that's exactly who we're interacting with right now. And so we just identify a problem, see if we can solve that for you in the upcoming months, and then I can chart a path forward to see how that can positively benefit your organization. So those are the kind of interactions that we enjoy having. Okay. Well, thanks again, everyone, for attending. Clint, thanks for your excellent preparation. Greg as well. Looks like we've got one last question
One
coming
more.
in before we let you go for the rest of your day. Can the lattice generated in Cubit be used for computation with the IGA solver? And is there a thermomechanic coupling in the IGA solver?
So yes, so the lattice generated in Cubit is we do the demonstration, the example that you saw of the model. Let's see, there it is. This example right here, this was done in Coreform IGA. So I think I hope that's answering your question. That yes,
And the lattice,
generate
was, yeah, and the lattice was built in Cubit too, as opposed to pulling in from somewhere else.
And then the thermomechanical coupling is a capability that we are currently working on. If you wanted to open up a conversation with us, we'd love to hear about what you have that might be causing you difficulties that Coreform IGA would be able to assist with.
Cool. Okay. All right. Well, thanks again, everyone, and have a great day.